Hi everyone, my name is Zain Abideen. Nice to meet all of you. I am a PhD student at TalTech University of Technology, and I am working on obfuscation technique, and I'm working under the supervision of Professor Samuel Pagliarni. Today I'm going to present an interesting and novel project named Design Obfuscation with Reconfigurable Logic. The outline of this presentation is divided into 9 different sections. First, I will present the introduction, and then I will introduce the design obfuscation concept and state of the art. Next, secure CAD flow using FDOM, block implementation, internal architecture, and results, security analysis, and finally the conclusion. Keeping the current situation, many semiconductor companies are following the globalized IC supply chain due to an evolving complexity, ever-shrinking time to market, skyrocketing cost of maintaining and building a semiconductor foundry. Consequently, there are few of the foundries that are equipped with advanced fabrication capabilities. Fabless companies outsource fabrication from third-party foundries. These third-party foundries are untrusted foundries in IC ecosystem due to the geographical and political issues. The globalized IC supply chain can create different security threats. A rogue element can pirate, insert malicious logic, reverse engineer, overproduce, etc. The aforementioned security threat could cause monetary losses, service interruption, can cause damage to data integrity. Moreover, it can also lead the device into the hazardous state where it can cause damage to the human being. To cope with the aforementioned security threats, the current countermeasures include split manufacturing, design camouflaging, logic locking, etc. Logic locking is an interesting technique, but still is evolving with time. The well-known attacks on logic locking include functional attacks and structural attacks. And concerning the functional attack, we have a SAT attack that is, and a lot of work is going on this type of attack. And concerning structural, we have signal probability, CQ-SPS, and sanitizer and fault injection-based attack, and many more. Regarding the design obfuscation concept, we have mainly exploited the reconfigurable logic as an obfuscation technique. This figure shows the 3 devices, FPGA, ASIC, and this project. If we concern about this device, FPGA offers a low performance, it is flexible, and it is fully reconfigurable device. It consists of the CLBs, and each has a lot flip-flop and max. On the other hand, we have ASIC, which is static, which has one-time placement, but it gives us best-in-class performance. If we come from the FPGA side and we try to approach the ASIC, we can see that if we slide from right-hand side to the left-hand side, the performance will increase because we're leaving the FPGA part and we're moving toward the ASIC, means we're approaching the ASIC, so we have the more performance. On the other hand, if we come from the ASIC side and we try to catch FPGA, then we are leaving the ASIC part and then we are increasing the FPGA, means the reconfigurable part. What it will do, it will increase the flexibility, and then it will also increase the obfuscation because the more part is reconfigurable. So in this project, the idea behind this project is that we produced a new device as shown in the center of this figure. This has the similar structure to the FPGA, you can see, and which has the flip-flop, and it will have a lookup table, muxes. But The lookup table will be reconfigurable, and it will be hidden, and it will be obfuscated. Concerning the state of the art, there are a few papers which are indirectly related to our work that are shown on the bottom of this slide. Regarding the first paper, the authors have exploited embedded FPGA using HLS approach to obfuscate the design. They have proposed the algorithm which selects a most vulnerable part that should be placed on embedded FPGA, and they try to keep it as small as possible so that they are not going to lose the performance. On the other hand, the authors have adopted a similar type of topology, and they divided their design into two parts. They call it ASIC and trap. And the trap is programmable, but instead of programming the logic gates, they have programmed the gates, and they obfuscated their design. For this work, we have opposed the recent practices, and we embed ASICs into FPGA. Our methodology comes in terms of a tool named FDOM, and we can see the device. If the FDOM produces this type of device, which we named as an embedded ASIC. It also provides a obfuscation space exploration, means that the designer can target for different obfuscation levels, and then he can analyze the behavior of the design. Recent practices split the design, and we also do the same. We split the design into two parts, ASIC and reconfigurable. Recent practice also performs security versus performance analysis, and we also do, and we have our tool has the capability to perform this kind of analysis during the design phase. The main difference is we come from the opposite side. We come from the FPGA. We assume in the start that we have fully reconfigurable device, and then we try to increase the ASIC part unless it achieves the specific criteria or it achieves a specific performance. This figure shows the secure CAD flow using FDOM. It has three phases. In the first phase, we synthesize the design using the commercial synthesis tools such as Vivado, and then we export the synthesized netlist and the timing report. In the second phase, the parser of FDOM reads the timing report and the synthesized netlist. Beside this is also need the information from standard cell library and the design target criteria. So it starts with the analysis of critical path, then it analyzes the critical path, and it extracts all the lookup table and their instances and their delays. And on the other hand, the parcel also reads the netlist. Then it extracts the primitives from the netlist. Then it specially decodes the lookup tables, and then it generates the value code for the combinational logic. Then it partitionizes the design into the reconfigurable ASIC look. Then this obfuscation engine starts replacing the reconfigurable cells with the static cells until it achieves the special value. It produces the ASIC design. Then we add the reconfigured branch, and it forms the embedded ASIC. Finally, it exports the area report, timing report, and the obfuscated netlist. In the third phase, we have a standard CAD flow, and you place and route the design, and we fabricate. Once the chip will arrive, we will program the chip, and the chip will be the functional. To achieve our obfuscation, we have exploited the combinational elements, and we have 6 types of the lookup tables, from 6 input lookup tables from 1 to 6, and we have given the high performance in the obfuscation engine to obfuscate obfuscate the loop 4, 5, and 6. and LUT 1, 2, and 3 are small, and they are ignored by obfuscation, and they will be treated in the place and route phase. We designed our custom LUTs for LUT 4, 5, and 6. We created these micros and implemented in Cadence Innovus, and we tried our best to be the compact micros with having the highest density, and the implementation layout of the LUT 4, 5, and 6 macros is shown in the following figures, and the implementation result is shown is listed in this table. Concerning the generic overview of the internal architecture of embedded ASIC, the internal architecture of embedded ASIC composed of the look, carry, mux, and registers. And because we are performing the combinational obfuscation, so in this figure we can see this part, the green part is the reconfigurable part, and the yellow part is the ASIC part. Here, as we obfuscated LUT 4 and 5 and 6, then this is a chain which is constructed from LUT 4, 5, and 6. So this is like a very big bit stream. And on the other hand, we have the LUT 1, 2, 3, 4, 5, and 6. But these LUTs will be implemented using standard cell. They are not more lookup tables. And the other necessary components for static parts, depending upon the design, memory, IO buffer, and maximum register. So here, this arrow, this obfuscation knob is shows that the obfuscation target. So if we move this knob, then this means that we are moving this green part and also the ASIC part. So total estimated area of the embedded ASIC is equal to A naught and AS, where A naught is the area of this reconfigurable part, and the AS is the area of this static part. Concerning the results, we have developed the preliminary version of FTOM, our custom tool. We have validated the proof of concept by obfuscating numerous designs. Then we have synthesized the design using Cadence Genius, and we have also verified the results using the simulation of gate level netlist. In this figure, we can see the obfuscation security versus timing performance trade-off. In this figure, we can see our security versus area trade-off. The x-axis shows the obfuscation target, means 45%, 50, or 55% obfuscation of the design. So 55%, like X% part of the design is obfuscated, and this is TNS and WNS. We can see that if we increase the reconfigurable part, so the TNS and DWNS also increases. So this means we are losing performance. On the other hand, if in this figure, we can see that if we increase the obfuscation, the area of static, means the ASIC part is decreasing, the area of the reconfigurable part is increasing. So by performing this type of analysis, the designer can get idea where he can achieve his targeted performance and security criteria. Regarding the timing and area information from FTOM, this is just a very simple and estimated WNS and TNS. More about the results, we have performed the similar analysis as shown in the previous slide for different design. Then we come to the conclusion that for some design, the performance improvements saturate very fast. For example, this table shows only 3 examples of different design. We can see that WNS is decreasing as we decrease the obfuscation. This means the performance is also decreasing. If we increase the obfuscation, the performance is also decreasing. And here it saturates and there is no more change in the WNS. So that's why we have explored obfuscation from 85 to 100% for different designs. The relationship between this saturation point and the performance is that it depends upon the structure of the design. It also depends upon the timing constraints and also depend upon the obfuscation criteria. In this section, we will analyze the security analysis and threat model that we evaluated for different designs. We assume that the threat model for our ESIC is like this, that adversary has an access to program device, such as an Oracle, and you can get this device or server. You can buy it from the market. And also, we also assume that an adversary can reverse engineer the netlist, and they have an access to reverse engineered netlist. The conventional set attack hardness depends upon two things, mainly on two things: the search space for distinguishing input patterns, dips, and also time to perform, time to exclude the one key or n keys in a single iteration. So we have some similarity to the logic locking. For example, one barrier, let's say LUT6, is similar to the 64 XOR gates in logic locking. In the same way, LUT5 is similar to 35 XORs, and LUT4 is similar to the 16 XOR gates in logic locking consequently. Consequently, we have performed an attack based on the structure and composition of different circuits. We assume that the goal of the adversary is to identify the masking patterns, mean the reconfigurable bit stream for single LUT, and to identify the functionality of the circuit. So the overview of attack is the design, or a reconfigurable design, is the function of KM, where KM is the bit stream to program the reconfigurable part, and ID is the input from for the design. And IASIC is the input from the ASIC part to the reconfigurable part, and IM is activation signal to activate the configuration mode. So KM is further function of different M1 to MN, where MN is configuration stream or masking stream for a single LUT. We strongly believe that adversary can exploit the structure of the design that is visible to the industry, like design ASIC, and adversary can learn different information by exploiting the frequency of the masking pattern and also the composition of different circuits. Regarding the structural attack, we have carried out this attack for MIPS and for arrays. And before we have extracted the frequency of different LUTs, and then we explore different distributions to fit our data, and around 5 different distributions. So we found that the data will be searchable for 3 different type of distributions. So in this figure, we can see the top figure has the x-axis, where this shows the identifier of masking pattern. And this is the frequency. We can analyze that let's say for identifier 775, we have a very strong and very high value, around 600. And then we have another value more than 200, and then we have value like more than 500. So this is like a decaying exponential behavior. So we can analyze that there are some of the unique masking patterns, but more of them are repeated many times. On the other hand, we can analyze the same behavior for RISC-V, and it has also like an interesting value. It's like more than 500. And by using the above frequency data, we have plotted the distribution. For the MIPS, we have plotted the distribution and the confidence intervals by varying the obfuscation targets. We can see that once we decrease the obfuscation, the confidence interval also shrinks. And the more confidence will have the foundry to, and we're leaking more information. In the same way, the same behavior is shown by the RISC-V. We decrease the obfuscation and we shrink the confidence interval. And this is the mean value. The result of the shrinking and expanding the confidence interval will give us the reduction in the size space of masking patterns. This will be explained in the next slide. Regarding the composition attack, we have carried out this attack on SHA-2 and RISC-V processor. And we have targeted the LOT6. Concerning the SHA-2, we can see that there is a high correlation between the crypto cores from 84 to 87, 84 to 86% obfuscation. This is this region. So in this way, the adversary can guess that what kind of the design is this, and he can guess the design. And there is also having the high correlation for crypto cores, DS and SHA, from 70% to around 84%. This has the same behavior, and this will also leak the information. So this and that. Moreover, if we consider this line, this shows a correlation between obfuscated and a non-obfuscated circuit. This concludes that if we obfuscate the design greater than 87%, then there is a very less probability that the adversary can learn from this composition. If we switch from 85 to 80% and 85%, then it will start learning, and it will increase. And on the other hand, there is an interesting result for the AES. This line shows the correlation between the obfuscated and non-obfuscated AES. We can see that if the design is obfuscated for 97%, then it has still the high correlation. Whenever we obfuscated the design AES greater than 97%, then there is no correlation. So the design is secure from the compositional attack. Moreover, the range 97 to 100 has some level of correlation from crypto cores. And if we go more than 90, if we decrease and go like 94 towards 0, then there is no correlation for any design. There is no correlation between the crypto cores, and there is a sum of the correlation from 82 to 0. And we also conclude that this type of attack also reduces the search space, and the search space, the reduction of the search space for this attack is more higher than the previous one. So we conclude the different attack, the previous two attacks in this slide. In this figure, we can see different levels, how the search space for one lookup table, this look 6, is shrinking by performing different attack. So the search space for lookup table 6 is 2 raised to power 64 patterns. If we if we compose and we collect all the design, we have used around 31 to 33 design in this experiment. Then we extract the unique masking patterns. Then it forms 3,376 masking patterns. So we switch from L1 to L2, level 1 to level 2. Once we perform the structural attack, from the probability distribution and confidence interval, we have frequency on the x-axis. From that frequency, we filter the masking patterns, and this reduces the search space from L2 to L3, and it becomes 426 for MIPS and for 393 for RISC-V. If we go more deeper, we perform the compositional attack, and adversary learns from the structure structure of the design that is obfuscated, and this reduces the search space, and he can means that once he gets the design, it will decrease the search space from level 3 to level 4. So we have the 69 and 45 masking pattern for SHA and AES respectively. In the future, we are more interested to work on any other attack, let's call XYZ attack, that will reduce the search space from level 4 to level 5. So the conclusion of this paper is that we have addressed the money issue of the hardware security. We successfully embedded ASIC into the FPGA that produces a new device called embedded ASIC. And our custom developed tool FTOM is an innovative way to obfuscate a design, and that produces the embedded ASIC. This also provides a design flexibility to the designer, where he can vary the FPGA and ASIC part, and he can analyze the different consequences by variation. This also provides an opportunity to analyze the performance versus security trade-off once the designer will vary the ASIC and FPGA part. Finally, we have obfuscated numerous designs such as AES, Kubik, Shake, and many other designs, and evaluated the security hardness against the aforementioned attack. Concerning the future work, we are working on the physical implementation, and then we will perform any other attack that will reduce the search space from level 4 to level 5. Thanks all of you. Any questions?